Good morning, good afternoon, good evening. Thanks for joining IBPSA webinar series. Today we have a webinar from a team of students. This is the first time we are having webinar based on student modeling competition, which gets organized every 2 years. And the subject of that student modeling competition is based on the local context where conference is taking place. I am very thankful to a team from Free University of Bolzano. They entered the modeling competition and they will talk about what they did. But before I hand it over to authors, I want to introduce a key person who managed the entire student modeling competition, not only just designing a competition, but over a period of 1.5 years, working with the students, trying to get some entries, trying to clarify question and answers from the students, and finally selection of the winners as well. Francesca Capelletti is a professor in one of the Italian university, and she put in a lot of efforts managing the student modeling competition along with the other colleagues of IBPSA. She also played a critical role in organizing a conference, which is just finished last couple of weeks back in Rome, very successful conference. I'll hand it over to Francesca to introduce competition first, and then she will talk about how they manage the modeling competition, and then later a team of students will present their entry. Over to Francesca.
Thank you very much, Rajan. Hello, everybody. As part of the 16th IBPSA International Conference and Exhibition, taking place in Rome, Italy, at the beginning of September, IBPSA organized a student modeling competition with the aim of providing a competitive forum for the youngest members of the building simulation community. And for this year's competition, the aim of the exercise was to use computer simulation to design the energy retrofit of an historical building located in Rome, Italy. So the primary goal of this competition was to find the most efficient possible retrofit design, given some constraints which were listed in a briefing document containing information also about the building and system characteristics, the occupancy density and ventilation requirements, the internal gains and schedules for occupancy, lighting, and appliances. So students had this sort of document, they can refer to it, and they had to follow some constraints. The competition was set up as a simulation pentathlon, that is a contest divided into 5 steps, which represent the tasks that a practitioner should go through when designing the retrofit of an existing building. These contests were specified into the document, and they were first, modeling and simulating the existing building. Second, assessing the building energy consumption and indoor environmental quality. Third, redesigning using retrofit measures to enhance the building performance. Fourth, assessing the building daylighting performance and visual comfort. And fifth, optimizing the building performance by means of parametric design, sensitivity analysis, or multi-objective optimization. In particular, the candidates had to take into account the historical features of the building, choosing those energy efficiency measures that could be applied without compromising the building historical value. And this was a very ambitious task. For this reason, teams' participation was encouraged, and appreciated. And in fact, we received 11 teams entries and only one individual participation. But also this last one was very good. So among these 12 entries of impressive quality sent from 6 countries all over the world, 3 finalists were shortlisted to present their work in front of a jury of 10 academics and researchers, experts of simulation of building energy behavior and indoor environmental quality. The finalists were a team from Carleton University, Canada, one team from the Free University of Bolzano, Italy, and the single participant from Rome, Italy. The criteria for the finalists selection were many. One was the accurate and intelligent use of building simulation, the methodology applied for building modeling and energy simulation, as well as the clearness of the environmental quality assessment, the metrics used, the quality of the retrofit design development, the capability in the daylighting and visual comfort evaluation, the methodology applied for optimized building performance, and the presentation and quality of the report. But moreover, part of the jury assessment was the final presentation and response to queries from the competition committee and the audience during a dedicated technical session of the IBPSA conference. The winners received free copies of the books Building Performance Analysis by Peter de Wilde and Building Performance Simulation for Design and Operation by Jan Hansen and Roberto Lamberts. So today, one of the finalist team, the team from the Free University of Bolzano, is presenting his work. And I have the pleasure to invite Nicola Franzoi to tell us about the competition. Thank you.
Okay, thank you, Professor Cappelletti, and thank you, Professor Raval. Hello, everyone, and thank you for attending the webinar. I'm Nicola, and together with my colleagues, Silvia, Pietro, and Clara, we would like to present you the project we submitted to the 2019 IBPSA student modeling competition. Before starting, I'd like to say that this project, together with the chance to present it in Rome, was a challenging and priceless experience. We had the opportunity to deepen our knowledge about building simulation, and we got in touch with the large community of IBPSA. Okay, that said, let's start with the presentation of the project. As Professor Cappelletti just said, the object of the competition is the simulation of an historical palace, and the competition is set up as a simulation pentathlon. Our vision to accomplish these 5 contests was to attempt the improvement of the performance of the palace, while also preserving as much as possible its artistic heritage. This has been possible using an optimization process that, other than minimizing the energy consumption and maximizing the environmental quality, it minimizes also the architectural impact of the retrofit. Moreover, to be consistent with the cost optimality approach suggested by the European Energy Performance of Building Directive, the well-known EPBD, we use the net present value to guide the choice of the optimal retrofit among the Pareto front resulting from the optimization. During the presentation, my colleagues will spend a few words to describe some interesting aspects of our project. How we evaluated the visual comfort, how we adopted the percentage of discomfort time to determine the heating system schedule, and eventually how we quantify the architectural impact of the retrofit design. One of the most challenging aspects we faced during the project was to realize a reliable simulation model. Indeed, the little information provided in the briefing documents forced us to make several assumptions. For instance, for what concerns the natural ventilation rates, we believed an airflow simulation would be far too detailed to obtain reliable results, given the little information we had. Therefore, we set up the ventilation rates equal to the minimum requirements, also in view of guaranteeing acceptable indoor environmental quality. However, this probably led to an overestimation of the actual consumptions, but it kept us on the safe side in the sense of not exaggerating the goodness of the retrofit design. A very important role in our project is played by the software we used. We started from two 3D models, one less detailed for energy simulation and the other one for lighting analysis. And we combined the power of Rhinoceros 3D modeling with the simulation kernels of Energy Plus, Radiance, and AC. The connection is enabled by Grasshopper, a graphical programming environment built in Rhino that combines the ease of performing tasks by coding with the simplicity of graphically doing it. But this connection wouldn't be actually possible without the Grasshopper plugins developed by Ladybug Tools, Honeybee and Ladybug. Especially Honeybee is very helpful in easing the setting up of lighting simulation with Radiance. So far we dealt with the first contest, Model and Simulate. Regarding the daylight performance, our analysis was based on two kinds of metric, static and dynamic. The most common static metric is the daylight factor, which is a good starting point for a first estimation of daylight availability, although it is assessed under CIE overcast sky. The daylight factor on average resulted lower than 2%, which is the target prescribed by the Italian law, and this suggesting somehow poor daylight availability. However, it is more appropriate to evaluate daylight availability considering a metric that accounts for skies based on weather data, such as a dynamic metric, for example, the useful daylight illuminance. As you can see in this figure, for a considerable amount of time, the illuminance level is below 100 luxes in many zones, and this enforcing what resulted from the static analysis. Therefore, we concluded that the use of sensor for integrating artificial lighting with daylight would be an unjustified cost, and rather we considered more important improving the energy efficiency of the lighting system. The UDI is also useful to preliminarily assess the risk of glare. Indeed, we expect that in those zones where illuminance surpasses 2000 luxes, glare is more likely to occur. Now I hand over to my colleague Silvia that will explain how we perform the glare analysis.
Yes, thank you, Nicola. As Nicola said, we started from the zones with the illuminance overcoming 2000 luxes to apply a first filter. We took the floors with the highest percentage, and among those zones, we consider the most critical orientation. The resulting zones are the second and third floor, north and south oriented. Then we apply to those zones the same approach. We run the annual daylight glare probability simulation by fixing a proper viewpoint. The red spots there in the figure of the carpet plot highlight the most affected hour by glare. Generally, they are located in the early afternoon during March and October. the annual simulation show that glare does not represent a big issue for our building. Nevertheless, by going into detail, we selected from the carpet plot the days with higher DGP value. And for those critical periods, we ran a point-in-time simulation. In this figure, at the right, we can see one of the considered viewpoints. For this case, the most critical period is the 50 October at 2 p.m., in which we detect a DGP value of 0.4, so perceptible glare. Even if the glare in this worst case is little and present only for a limited time, we explored the usefulness of shading device. We assume that the building has already external shutter, but this means that the shading behaves like an on-off system, and so it is not possible a dynamical control by the users. For this reason, we model internal removable Venetian blinds. This solution, the Venetian blinds, improve DGP for the case that is shown in the slide, improves DGP from a value of 0.4 to 0.37, with blinds halfway closed. In this way, we succeed both in finding a solution that does not affect the artistic heritage of the building, and also in managing the daylight availability, and so glare risk. To conclude, with this solution, it is possible to guarantee the visual comfort of the occupants by means of a dynamical controllable device, at also an affordable cost. That's obviously it's really important. Now I will let Nicola proceed with the analysis. Thank you.
Well, thank you, Silvia. Okay, well, visual comfort is part of the indoor environmental quality, together with thermal comfort, which we evaluated adopting Funger's and adaptive models as defined in the European standard 15251. The adaptive model is necessary to determine the comfort conditions outside the heating season. In fact, the building isn't provided with a cooling system. And to perform the long-term evaluation outside the heating season, we adopted the weighted discomfort time, which indeed weights the hour of discomfort by how much the operative temperatures falls outside the comfort range. We didn't really have to evaluate comfort during the heating season, as we knew from the briefing document that it was guaranteed. However, we are going to see how this clue was helpful in the assessment of the energy consumption. Pietro will tell you something about that.
Yeah, thank you, Nicola. And well, the challenge was to set up the heating system, having no idea about how it works and how effective it was. In fact, we knew its structure, its main components, but no information were given about its schedule. As a consequence, it was impossible for us to compute the energy consumption of the building. It was like a dead end. A hint to the solution to this enigma comes from the briefing document, which states that the thermal comfort during the heating season is satisfied. And that was our key point. Well, to do so, we firstly sized the system during the design day of the weather file. Then we tested it, following an iterative process as reported in the figure. We guess a first schedule, we run the simulation, and we compute the whole building percentage of discomfort time. We then adjusted the schedule until the PDT falls within the acceptable deviation of 5%, according to the European standard 15251. We agreed together that the actual building, the as-is building, belongs to category 3 of the standard. As a result, we obtain the heating curve as reported in the figure on the right. As you can see, we have a setback temperature of 18 degrees until 2 hours before the building occupancy. From that time on, a set point of 20 degrees is scheduled. During the weekends, it is not reported here, but the setback temperature lowers to 10 degrees Celsius. We can note that the setback temperature is quite high, 18 Celsius degree. We are pretty sure that this is due to the high thermal inertia of the building. Indeed, a lower setback temperature would not respect the required deviation. Okay, the next figure shows the percentage of discomfort time for all the classes and offices of our building. We can appreciate that the building PDT, shown as the dotted line, is approximately 2%, so thus lower than 5% as required. The IPDT that the circles surround correspond to the classes and offices of the last floor. And the IPDT is due to probably to the poorly insulated roof. Okay.
Thank Pietro. Up to now, we have developed a model, assessed the building daylight availability, visual comfort, and we have introduced the thermal comfort metrics. However, to complete the second task, we have to assess the actual building performance, which is now possible having defined the schedule of the heating system. This slide presents a summary of the energy consumption of the actual state building. The left-hand chart shows the monthly energy balance of the building, and the pie chart on the right shows the share of annual primary energy consumption. These two charts gave us clear insight into the main issues of the actual state building. For instance, the pie chart highlights that there is considerable consumption due to lighting. And moreover, solar and lighting gains outside the heating season are the main source of overheating, causing more than 3,000 degree hours of discomfort. Well, there is room for improvements. Improvements that, according to our vision, should improve the energy efficiency, enhance thermal comfort outside the heating season, and last but not least, preserve the building artistic heritage. That said, we identified few energy efficiency measures that improve building performance without affecting its heritage. One of these measures is clearly substituting the existing light bulbs with LEDs. And furthermore, a significant reduction of the weighted discomfort time outside the heating season could be achieved by simply increasing ventilation during night hours, the so-called night-free cooling. And to further limit the risk of overheating, external shielding devices can be effectively used. However, they usually have a fairly high architectural impact. That's why we considered to adopt the existing external shutters to limit the solar gains during critical hours. These measures do not affect the artistic heritage, and their effectiveness is such to justify their cost. So we consider these interventions necessary, such as to form a baseline set common to all the following retrofits. Well, so far we have obtained an intermediate retrofit that, of course, could and actually need to be expanded to include common energy efficiency measures, such as the windows refurbishment or the envelope insulation. However, these kind of interventions usually clash with the safeguarding of the artistic heritage. Therefore, they should be preferably considered within an optimization process that has as objective also the minimization of the architectural impact. But how can we compute the architectural impact? I'll let Clara tell you how we evaluated the architectural impact.
Thank you, Nicola. Well, quantifying the architectural impact, as you can imagine, is not trivial, and clearly to establish the negative effects of a retrofit is fundamental a multidisciplinary team. Thereby, this work relies on the study developed by Roberti et al. The authors evaluated the heritage impact of typical energy efficiency measures involving a team of 10 heritage experts. Specifically, the evaluation is based on 3 aspects of the building component that should be safeguarded: visual, physical, and spatial. The heritage experts were asked to grade the relative importance of preserving these 3 aspects for a generic historical building. The marks were then converted into conservation weights by means of an analytic hierarchic process. After having selected a case study building and a possible set of measures, a team of local heritage experts was asked to establish whether each of the outlined measures would have preserved or not the 3 aspects of the building components. Eventually, the conservation score of each energy efficiency measure is the sum of the conservation weights previously defined and reported in this table on the left. So, to recap, to compute the conservation score, hence to quantify the architectural impact of an energy efficiency measure, we need 3 ingredients: identify our case study building, get us the table with the conservation weights, call on a team of local conservation experts. Considering the insufficient knowledge of the case study building, it was not possible to compute the conservation score for this palace. Thus, we adopted the same reported in the cited paper, expecting them to be conservative, since computed for a more prestigious building with frescoes and stuccos. The need to adopt these conservation scores constrains the energy efficiency measure considered to the same outlined by the authors, and the planned interventions are reported in this table. Eventually, we define the architectural impact of a retrofit solution composed by energy efficiency measures as in this equation, to point out how much a retrofit measure is degrading the artistic heritage rather than how much it preserves it.
Okay, thanks, Clara. We are now close to the end of the design process, the optimization. The heavy preconditioning of the optimization parameters led to a search space of just 135 retrofits, allowing us to use brute force optimization. Here we have a chart representing the search space in the Pareto set, with a color scale highlighting the third objective, the WDT, weighted discomfort time. And this sort of hyperbolic displacement shows the concurrent nature of the architectural impact and the annual primary energy. Moreover, the stars display 3 retrofits that we identified as potential optima. You probably see just 2 of them because one of the optimal retrofits is eaten by the other, as we will see later on. This in this slide, we reported the data of we reported the graph, the chart of the Pareto set in 3D. So we have the 3 objectives, and as color scale the net present value that we used to select the potential optima that again are displayed by stars. And in this case, you will see clearly just one of them because one is hidden by another retrofit of the Pareto front, and as before, 2 of them are overlapping. And this is clear in this slide. That report is a summary of the data regarding the 3 optimal retrofits. Optimum number 1 as the maximum net present value and consists only of insulating the roof on the inner side with rockwool. The third one is just like the first, and here we explain why two retrofits were overlapping. But using wood fiber instead of mineral fiber results in a more expensive and so thus a lower net present value retrofit. The second optimum has the greatest improvement for the annual primary energy consumption. But not only the architectural impact is worse, but also the weighted discomfort time isn't improved as much as in the first case. And this is because the window replacement lowers the ventilation rates during the night hours in the summer season, leading to more degree hours of discomfort. So considering our vision and the economic feasibility, we agreed in selecting the first optimum as our retrofit design. So I'd like to conclude saying that our design consisting of the lighting system refurbishment, night-free cooling, the use of existing external shutters together with removal of Venetian blind and the insulation of the roof is proven to reduce the annual primary energy consumption, considerably improve comfort condition outside the heating season, exclusively by means of passive strategies, achieve the economic feasibility, improve visual comfort, all these preserving the artistic heritage of the building. So thank you for your attention. We will be pleased to answer any question.
Thank you.
Thank you, Clara, Nicola, Pietro, and Silvia. Why audience ask query and comments to question available on your panel. Type question required. I'll ask. Do you have any questions from the audience? Or okay, so let me one. I post this to all four of you. One of you can respond. How easy it was to. Okay, somebody can't hear. Can you hear me now? Hello, am I audible? There's a question coming up. What tool did you use for optimization process? Question is, what tool did you use for optimization process? Nicola, would you like to answer what tool did you use for optimization?
Okay, sorry, the audio wasn't very clear, but I got the question. As said, we used brute force optimization, and we generated the search space adopting J+, which is a software for parametric analysis. We basically defined the parameters that could vary, and we generated the 135 jobs, Energy Plus IDF files, input data file. And then we used, again, J+ to launch the simulations, which took approximately 7 hours of 7 computational hours with a hexacore computer. And then we elaborated the results with a script in MATLAB that allowed us to define the Pareto front and to post-process the results. Was it clear?
Yes, thank you. That question that was a question from Dima, and also there is another question which let me ask. Was there any consideration for integration of renewable energy? That was one question. I suppose the design brief was not asking to integrate renewable energy, but was there any consideration in inviting?
Excuse me, it wasn't
Right.
Nicola,
the question was that did you consider renewable energy production?
Well, we did consider of installing PV panels, given also the favorable location. South of Italy is usually very sunny, and we did consider it, but given the little information in the briefing document, we thought that the installation of the simulation of PV panels would be just speculation, because we didn't know exactly how the heating system was, and so we decided to not to go into the details of the heating system, and actually we consider also that electric energy from PV panels would be much more important, much better if we had installed a heat pump rather than keeping the gas boiler already present in the building. Yeah, but basically we didn't do it because we didn't put much effort into the simulation of the system, because again the details provided were not enough to obtain reliable results with the simulations.
Thank you. Let me ask Francisca. Was the renewable integration was part of the briefing document?
I'm sorry, Rajan, I cannot hear you very well. Can you repeat, please?
Was emphasis given to integrate renewable energy sources and simulation of renewable energy desired in competition?
No, I'm sorry, Raval. The connection must be disturbed, because we don't get any words.
Okay, so yeah, so can you hear me now?
Yeah, now yes.
Yes. So the question was that was there any consideration in the design briefing document itself, the brief which was given to the students, was there any requirement of simulating renewable energy source? The question was for Francisca.
Okay. Thank you for the question. Well, actually, when we prepared the briefing, we also thought about the possibility of installing PV panels or solar panels on the flat roof. There is a part of the roof that is flat. So we thought about this possibility. Yes, but of course, we did not suggest this intervention. We prefer to give students a freedom, to give some freedom in deciding the best interventions, the best energy saving measures, because yes, some teams could be more good in system design, and some other teams could be better in some other fields. So we did not provide many information to give to let the students free of propose energy saving measures and design solutions.
Okay, that was helpful. We don't have any other question, and I would like to thank the team again. Great work. And I'm also thankful to Professor Francisca for guiding the whole process of modeling competition. And congratulations to the team as well. With this, I'll end the webinar, and the next webinar also would be based on student modeling competition, which hopefully we'll be able to broadcast in the second week of October. Thank you very much.
Thank you.
Thank you.
Thank you.